All right, so welcome to this class where I'll be discussing this new topic that we're calling electric forces and electric fields. So this is a very important topic, and by the end of this class, I would love us to understand the invisible electric interactions that are mostly shaping our world, from electronics, the communication systems that we use each and every day, and also electromagnetism. So it is going to lay the groundwork of all these things that we see in our everyday lives. Electricity. Every day we use electricity, and it is all starting from these small things that we're calling electric forces, thereby having a electric field. So by now, ladies and gentlemen, I'm sure we understand to say each and every object is made up of matter, and matter is made up of what we call atoms. And these atoms are very small, and they have what we call subatomic particles. They are mainly three subatomic particles. There's what we call protons, there's what we call neutrons, but also what we call electrons. So from our biology, from our chemistry, we already did atomic structure, and I'm sure by now we know to say uh, protons and neutrons are found in the nucleus, whilst the electrons are found in what we call electron clouds, or what we call in energy levels or shells, whatever you can call them. It just basically means the same. So we said these protons and neutrons that are located on the center of the atom are the ones that carry almost the whole mass of the atom. And we said the mass of each one of these guys is 1 Dalton, or 1 atomic mass unit, 1 AMU, 1 atomic mass unit. Even the neutron has a mass of 1 atomic mass unit. And for the electron, we say the mass of an electron is very small, such that we just say it is negligible. So if we convert this 1 atomic mass unit, or 1 Dalton, into kilograms, we are going to notice that this is directly translating to 1.67 times 10 to the power minus 27 kilograms. This is how small the mass of a proton is. And the same is the case when it comes to a neutron. Hence, the whole mass of an atom being concentrated on the nucleus. Also, when it comes to the electron, the mass of an electron is just about 9.11 times 10 to the power minus 31 kilograms. And you can tell to say this is actually much lighter than the protons and the neutrons that are located in the nucleus of our atom. This is about 1,800 times smaller than the electron that we have in the nucleus of our atom. Hence, we just say the mass of the electron is actually negligible. We say the mass of our electron is um, negligible. So we also talked about the protons and the electrons having charges. We said the neutron is neutral. It doesn't carry a charge, but when it comes to protons and electrons, they carry charges. So a proton carries what we call a positive charge. Whilst an electron, which is located in the electron shells, carries what we call a negative charge. And as usual, the neutron in this case is just neutral. It doesn't carry any charge. And we're going to notice to say the charge of or the size of the charge on a proton and electron is basically the same. So the charge, or the size, the magnitude of the charge that the proton has is basically the same with the charge, or the magnitude of the size, or the magnitude of the charge that an electron has. They have the same magnitude, or the size of these charges are actually the same, and we call them an elementary charge. Elementary charge, and this is represented by a small letter E, like this. So the magnitude is the same. What is different? The different is the sign of the charge. It can either be positive if you're talking about a proton, or it can be negative if you're talking about an electron. So if it is a proton, we're going to say this is what? This is a positive E. the same magnitude, whilst if it's an electron, we're going to say this is a negative E, like that. Hence, in most cases, if we are describing an electron, you're going to find that there's a negative E somewhere. Even when you're describing a proton, you're going to find a positive E somewhere. The magnitude of these guys is basically the same. The only thing different is that one is positive, whilst one is negative. So this magnitude of a charge is measured in what we call coulombs. The coulomb is the SI unit for the measurement of charge, or the amount of charge. And the coulomb is represented by the capital letter E, or the capital letter C rather. And it has a magnitude of what we call, the magnitude of E is actually 1.60 times 10 to the power minus 19 coulombs. This is the magnitude of an elementary charge E. So E has that magnitude, and this E can either be positive or negative, depending on what you're discussing, whether you're discussing a proton or an electron, respectively, in that manner. So with what we've been talking about in this class, I'm sure by now you can tell to say there are only two charges that are in existence. There's what we call the positive charge, but also what we call the negative charge. So there are some simple rules that we're supposed to remember following what we call the charge model. Let me just write it down here. Following what we call the charge model. And this model basically explains to us, or basically just gives some simple rules that we are supposed to follow when we are discussing charges, or when we are describing charges, or when you're talking about charges. We're not to say we only have two charges in existence, or there are only two charges that exist, and that is a positive charge, the positive charge, and a negative charge. These are the two charges that exist. So what rules must we follow? We have to remember to say two charges that are of the same kind are going to repel each other. So if the two charges are the same, it doesn't matter whether those two charges are negative or those two charges are positive, so long as they are the same. Let's say they are both positive, they are going to repel each other. If they are both negative, they are also going to repel each other. So I can just say similar charges repel. Similar charges repel, whilst the opposite charges attract, like that. So when you are having similar charges, it doesn't matter whether those two charges are both negative or those two charges are both positive, they are going to repel each other. But when the two charges are opposite, let's say you have one positive charge and one negative charge, the two opposite charges are actually going to attract each other or pull each other together. So sometimes even when you're talking about a neutral object, because if something is neutral and you say that thing is made up of atoms, if it is neutral, that means it is having the same number of what? The same number of protons, but also or rather, I can just say the same number of protons and neutrons. So if that number is balanced, that particular object is going to be neutral. So even in neutral objects that do not have a net charge, meaning they have the same number of protons and and electrons rather, these guys can be attracted to objects that are charged. You can either say that object is positive or that object is negative. Like here, let's say if we have this positive charge, then you introduce it to an object which is neutral, which has no net charge. You're going to notice that that object which is neutral is going to be attracted to the charged object. Why is it getting attracted to a charged object whilst it's neutral itself? It's because it is going to follow what we call the principle of polarization. It is going to get polarized. What do I mean? It is made up of electrons and protons. So if a charged object is introduced, you're going to notice that there will be a difference in concentration between the positive charges and the negative charges of that particular neutral object, such that one particular end is going to become more positive and one particular end is going to become more negative. And the opposite charge to this charged particle that has been introduced is going to get attracted to this charged particle that has been introduced. Why are we having that? Is because the neutral body has been polarized or polarized. I can put it in that manner. So we're having a difference in the concentration or in the net concentration of the charges. One end becomes more positive, whilst one end becomes more negative, hence an equal distribution of the charges. And the opposite charge is going to get attracted to the charged particle that has actually been introduced. So it's the same thing that happens mostly when you look at you get a balloon. Let me say, for example, you get a balloon, then you start rubbing it in or in your head, rubbing it against your hair. You're going to notice that it is going to pick up some of the negative charges and stick to a neutral wall because it pulls the wall's charges slightly. It is going to polarize the other end. Hence, you're going to notice the sticking together. The opposite charges are actually getting attracted, and that is how it is going to work, ladies and gentlemen. But just like energy, I would love us to also understand to say charges are also, or rather, charges um, also get conserved using what we call the conservation of charges. Conservation of charges. And what do I basically mean when I say the conservation of charges? So the law of conservation of charge just tells us to say the charges that we've been talking about cannot be created, nor be destroyed. No, be destroyed, but it can only move from one place to another. The example that I've already given you is an example of a balloon. When you rub a balloon, let's say in your against your hair, the electrons are going to move from your hair to the balloon, making the balloon negative and the hair positive. But the total charge is basically going to stay the same. It's more like you're just transferring money from one account to another, but the net amount in those accounts is basically the same. There's no change. It's the same principle that we're going to apply actually here. So what if we have two charges in the range of each other? Let's say we have two charges, they might be the same charges or opposite charges, but they're just in the same plane, in the proximity of each other. For example, I can say maybe here I have a charge that I can call Q1. Even here, I have another charge that I can call Q2. So how are these charges going to behave towards each other? Because we've been talking about the attraction and repulsion of opposite charges and like charges respective. How does that happen? So this phenomena is explained by what we call the Coulomb's law. The Coulomb's law. And what we're supposed to understand is that each and every charged particle creates an electric field around it. And this electric field that is produced by each and every charge is the one which is responsible for the push or the pull of other charges that are in the range of it. So if it is an opposite charge, as usual, it is going to be pulled towards that particular charge. Whilst if it's the same charge, it is going to be pushed away. So all those interactions between charges are happening due to what we call electric field or electric fields that are created around each and every charged particle. So the Coulomb's law actually tells us the electrostatic force between 2-point charges. Let's have a charge here. I can call this Q1 as usual. Then I have another charge there. And let's call this Q2. The electrostatic force that is between these two charges is the one that is going to be defined as what? As the Coulomb's law. So this electrostatic force can be measured or can be calculated using this formula, the Coulomb's law, electrostatic force. This is basically equal to, or actually equal to K, which we call the Coulomb's constant, Q1 multiplied by Q2 over R squared, where R squared is the actual distance that is between our 2-point charges. So what do we mean when we say 2-point charges or a point charge? A point charge is just a particle that has a charge but is too tiny such that it doesn't have size. So I can say, or I can just describe it as a tiny object with charge but no size. That is what we call a point charge. So this Coulomb's law actually applies on what we call point charges, but you can also apply it on things like charged spheres, but it should be under a condition, and that condition is that the charged spheres that you're applying this formula on should have a smaller size compared to the distance that is between those two charged spheres or charged particles. So that's the only way you can apply this law that we call the Coulomb's law. So this K that we have in our formula here is what we are calling the Coulomb's constant. And the Coulomb's constant K has a value of 8.99 times 10 to the power 9 uh, newtons meter squared c squared. That is the value of our Coulomb's constant, but it can also be written in another form. We can say K is equal to 1 over 4 pi 4 pi. Then we have our lowercase epsilon there, and our lowercase epsilon also has its own value, which is 8.8 by 10 to the power minus 12 to the power minus 12 c squared over newtons m squared, like this. So that is the value of our epsilon. So the Coulomb's constant K can be in this form or that form, but in most cases you're going to find that we just use this form, which is already in a simplified manner, or which is already in a simplified form. But sometimes it is also going to be written to the closest whole number, such that you only find the 9.00 times 10 to the power 9 newtons meter squared per Coulomb squared. That's the form in which you are going to find it. So that, ladies and gentlemen, is the Coulomb's constant, and this is how you can calculate the electrostatic force that is between these two stationary point charges. And the charge, or the electrostatic force that is between these two stationary charges, is going to be in a manner that we call an action reaction pair. So the forces are in an action reaction pair. You remember, using Newton's third law, what we basically mean when we talk about an action reaction pair is that they are equal in size but opposite in direction. So the electrostatic force that is between these two point charges is going to be equal in magnitude but opposite in direction. So the force that Q1 is um, exerting on Q2 and the force that Q2 is exerting on Q1 will be the same but opposite in direction. And that, ladies and gentlemen, is how we can calculate the electrostatic force that a certain charge is exerting on another charge that is within its range using Coulomb's law. But in most cases, you're also going to find that charges are in what we call or are superimposed on each other. Okay, or I can say they are in what we call the principle of superpositioning, such that there will not only be one charge exerting an electrostatic force on another charge. Let's say maybe there are two or three charges that are exerting an electrostatic force on another charge. This principle that we call principle of superpositioning. I can just write superpositioning. I hope you remember. Superpositioning. That means we have more than one charge which is exerting an electrostatic force on a particular charge. So you might find that maybe another charge is there, another one is here, and another one is here. This one might be Q1, Q2, and the Q3 there. So you can tell to say these charges are actually existing in different axes. This one might be positive, negative, and positive, or whichever way they can be. So long as they're in that manner, we can say they are superimposed on each other. So how do you calculate the net force on such charges? So when the forces are superimposed, the total force on one charge is actually the vector sum of the individual forces that we have here, which means we're supposed to apply the knowledge that we learned on vectors. I hope you haven't forgotten about that. So we can give an example on superpositioning. If you want to find the net force, F net, let me use black. We're going to use our knowledge on vectors such that the F net, the net force on one charge, will be equal to the vector sum of the other individual forces that we have in your axis. So I can say Fxy plus Fy squared like that. And you can also calculate the direction using the tan inverse rule. We have your Fy over Fx there. And that, ladies and gentlemen, is how you can calculate the net force in a case where you have superpositioning or where your charges are superimposed. So one thing you should also know is that the sign of the electrostatic force can depend on the charges that you're dealing with. If the charges are positive and negative, like in this case, the example that I gave, Q1 is positive and Q2 is negative, you're going to find that your electrostatic force is going to be negative. And if it's negative, that means there is a force of attraction. That means the electrostatic force that you've calculated is basically a force of attraction. Whilst if the two charges are the same, let's say they're positive and positive or negative and negative, the electrostatic force is going to be positive. And if the electrostatic force is positive, that means it is a force of repulsion. So that is what we should keep in mind, ladies and gentlemen, using the Coulomb's law. We're going to see in a short moment. We're going to look at examples so that we can see how the Coulomb's law is applied in answering questions, the application of the Coulomb's law in both superimposed question or questions or superimposed charges or charges that are in the same line, or rather just two charges interacting with each other, or superimposed charges where we have multiple charges exerting an electrostatic force on one particular charge, and we're supposed to find the vector sum of those individual charges in order for us to find the net electrostatic force on that particular charge. So that, ladies and gentlemen, is how we can use the Coulomb's law to explain how different charges interact with each other when they are in range of each other or when they're in proximity of each other due to the electric field that is produced by each and every charge, or that surrounds each and every charge. So we said every charged particle actually creates an electric field around it. And to say this is the field which is responsible or can be able to pull or push other charges. So what do we think is an electric field, or what is the actual description, or how you can describe what uh, an electric field is? So in simple terms, we can just say this is an invisible region because you cannot actually see it, but it is there, it is existing. So an electric field is just an invisible region around a charge where other charges are going to experience a force. The imaginary, or can I say not imaginary, but an invisible region around a particular charge where other charges are going to experience a force is what we call um, uh, an electric field. So an electric field is actually measured using what we call electric field strength. And the electric field strength represented by E, the electric field strength represented by E at a point is the force per unit area, per unit positive charge placed there. The electric field strength E at a point is the force per unit positive charge placed there. So it can be measured using the formula or calculated using the formula E is equal to F over Q, like that. And F there is a vector and it is representing electrostatic force. F is the electrostatic force, and since that is a vector, that means our electric field is also going to be a vector. And the SI unit for electric field is actually newtons per coulomb, like this, or volts per meter. So you can also write it as volts per meter or newtons per coulomb, depending on the units that you are actually using. So E is electric field strength itself, whilst F is the electrostatic force on a charge in newtons, and Q there is giving us a charge. But this charge that we're using here is a test charge. It's imaginary. It doesn't change the field. So it's an imaginary charge. So we can just call it a test charge, which is in Coulomb. So the SI units for electric field strength is actually in newtons per coulomb using those units that we've talked about there. And we can see to say since the electrostatic force is in newtons, or it's a force, it's a vector. That means even the electric field itself is supposed to have a direction. Electrostatic field or electric field is actually a vector which has a direction. So this direction is actually where a positive charge would be pushed. And what does that mean? That means if I'm given a charge here, which is positive, the electric field on this positive charge is always pointing away from a positive charge. So that means at 90 degrees from this positive charge, there's always electric fields like that. So that is the direction of electric field on a positive charge, and it is represented using these lines, these imaginary lines that we call electric field lines. These lines are just there to to show the direction and strength of the electric field, and there are some rules that are supposed to follow when you're drawing your electric field, your electric field, the field lines. So since we've said the electric field is always pointing away from a positive charge and pointing towards a negative charge, which means if I have a negative charge here, let me write it in red. If I have a negative charge here, the electric field will be pointing where? Will be pointing at 90 degrees towards my negative charge from all the directions, like that. So that's how we can show or depict electric fields. We can visibly detect them or visibly show them, illustrate them using what we call electric field lines. And these electric field lines are drawn using some set of rules such that they always start at a positive charge and end up at a negative charge, which I've already shown there. The arrows point the way a positive charge would move, and they never cross each other. And the density of the lines is also going to represent the strength of the electric field that you have at a certain charge, which means when the density is more, you have a lot of lines closer to each other. That means there is a lot of electric field compared as when you have uh, sparsely shown lines or sparsely drawn lines. That means there is a smaller density of electric field at that particular point. So this is the formula that we can use to calculate electric uh, the electric field. I said the electric field is equal to electrostatic force over Q, which is a test charge. But from here, I'm sure you can tell to say the force on a charge in an electric field, E, this force on a charge in an electric field can also be calculated. And how can you calculate that force? It's yeah, so using this formula, I'm sure you can tell to say we can calculate the electrostatic force or the force on a charge in an electric field. This guy, the force on a charge in an electric field using this same formula. We're just going to make force the subject to the formula, the electrostatic force, the subject to the formula. I'll say over one, then I'll cross multiply, and then we're going to get F, which is the force on a charge in an electric field, being equal to Q multiplied by electric field strength, like that. So this is how we can calculate the force on a charge in an electric field. And you're going to notice that if Q is positive, which means if the charge is positive, the force is going to be in the same direction as the electric field. So let's say if you have your electric field pointing in that direction like that, then you introduce a charge there which is positive. The the force is going to be in the same direction with the E, which is the electric field strength. If your Q is negative, you're going to notice that the force is going to be in the opposite direction with the electric field strength. So the this guy there is going to be pointing in the opposite direction as E if your Q is negative, and it is going to be pointing in the same direction as E if the Q that you have or the charge that you have is positive. And this force can make a charged particle speed up or sometimes even slow up. That, ladies and gentlemen, is how we work around the electric fields or electric field strengths. And that's the relationship between electric field strength and the force experienced on a charge in an electric field. That is how we can calculate that, ladies and gentlemen. So let's just, how about electric field of a point charge? So from the Coulomb's law that we already looked at, or that we've already looked at, you're going to notice that if you have a distance r, let me just say electric field on a point charge. So what does that mean? That means, let's say you have your electric field there, then you introduce a point charge uh, in the range of that electric field. So from the Coulomb's law, the field at distance r from the charge q is going to be equal to E, which is the electric field, equal to K, which is the Coulomb's constant, Q, which is the actual charge you're dealing with, over R squared. So the direction is always going to be away from the positive charge and towards the negative charge. And here, it's not going to be constant. It is going to get weaker as the distance is increasing, whilst it will get stronger as the distance is reducing, using what we call the inverse square law that the Coulomb's law actually follows. That means if you double the distance, the force is going to decrease to a quarter. Whilst if you reduce the distance by half, the force is going to quadruple. Then that's how it works. So if you have uh, or if you have a point charge introduced in an electric field, you're going to notice that the field at that particular distance from the charge is going to be equal to K multiplied by the magnitude of Q, which is the actual charge, over r squared, which is the distance between the source of the electric field and the charge itself. So that is that, ladies and gentlemen. And the next time we meet, we'll talk about uniform fields and parallel plates, and also motion of charged particles in electrical fields. Thank you very much.